Hello everyone, my name is Lahari and I am from CSE Regular. Today I am going to explain about first order RC circuits. Basically, what is a first order RC circuit? So, an RC circuit is an electric circuit that contains a resistor and a capacitor which may be powered by a voltage or current source. These RC circuits are used to study how capacitors behave when connected to a battery and how circuits respond to voltage changes. Okay, but why is this circuit known as first order? First order indicates that this circuit consists of a single storage element. It may be either inductor or capacitor, but here we are dealing with capacitor. So this is known as a first order RC circuit. The key concepts which are involved in RC circuit are voltage across resistor and capacitor, current across resistor and capacitor, time constant, exponential growth and decay, and graphs. What are the components of RC circuit? The first component is resistor. What is a resistor? Resistor is defined as a passive electrical component with two terminals that is used for either limiting or regulating the flow of electric current. That means it opposes the flow of electric current or resists the flow of electric current in the circuit. And the main purpose of this is to reduce the current flow or lower the voltage in any particular portion of the circuit. And now this picture is a resistor. And now what is a capacitor? Capacitor is a passive electrical component with two terminals and has the property of storing the electrical charge, and also it opposes the sudden change in voltage. It consists of two metallic plates or electrodes, and are separated by a dielectric. And this circuit also consists of a power source. Often a DC voltage source is used to charge and discharge the capacitor, which influences the time dependent behavior of current. Now there are basically two types of RC circuits. That is, one is series RC circuit and one is parallel RC circuit. This circuit consists of capacitor and resistor in series. So this is called series RC circuit. As we know, in series the current across the resistor and capacitor is same, but the voltage changes. And in parallel circuit, these resistor and capacitor are connected in parallel, and the voltage across these two is same, the current changes. Now in series RC circuit, let us deal with how individual resistors behave, individual capacitors behave, and how the combination of resistors and capacitors together behave. In resistors, the basic formula of resistance is rho L by A, and how to calculate the series resistance, it is R1 plus R2 plus R3 plus so on, etc. And in parallel, the effective resistance is given by 1 by R effective is equals to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on. And voltage across the resistor in DC circuit is equals to I into R. That is the Ohm's law. And in capacitors, if these capacitors are connected in series, then they are added as 1 by C effective is equals to 1 by C1 plus 1 by C2 plus 1 by C3 and etc. And when these capacitors are connected in parallel, then they are directly added. That is, C effective is given by C1 plus C2 plus C3 plus so on, etc. In RC circuit, that is in combination of these both, in charging condition and discharging condition, there are two kinds of conditions. During charging condition, Q of t is given by Q naught into 1 minus e power minus t by RC, and V of t is given by V naught into 1 minus e power minus t by RC. V naught and Q naught are maximum values, and during discharging, we see that Q of t is equals to Q naught into e power minus t by RC, and V naught is equals to V naught into e power minus t by RC. Time constant is given by resistance into capacitance, R into C. Now first let us take the case of charging of capacitor. To derive this, we will consider a circuit with resistor of R ohms, capacitor of C Faraday connected in series. The initial condition of circuit is that the time is equal to 0, charge is equal to 0, and current is equal to 0. When the switch is closed, the time will start from t equals to 0 and the current starts flowing through the capacitor and the resistor. An initially uncharged capacitor can be assumed to be a connecting wire just after the circuit is completed. So, as we know that capacitor opposes the sudden change in voltage, it behaves as short circuit at transient condition and it behaves as an open circuit in steady state condition. At time t equals to 0, the potential difference across the capacitor is equals to 0 and continues to be equal to 0 just after the time t equals to 0 also, just until a particular time. This is the circuit which we are going to take for the derivation of charging and discharging both of them. When the key is pressed, the capacitor begins to store the charge, and if any time during the charging I is the current through the circuit and Q is the charge on the capacitor, then potential difference across the resistor is given by IR and potential difference between the plates of capacitor is given by Q by C. We know already the formula that Q equals to CV. From that, the potential difference is equal to Q by C. Since the sum of these potential is equal to E, we are considering the total voltage across this across this circuit is E. That means Ri plus Q by C is equals to E. And as the current stops flowing when the capacitor is fully charged, it becomes what? Open circuit. The current flowing is equal to 0. So at that condition, Q is equal to Q naught, the maximum value of charge on the capacitor. And I is equals to 0. That means the current is now not flowing. From equation 1, we can get that Q naught by C is equals to E. As I equals to 0, if we substitute in 1, then we get that Q naught by C equals to E. From equations 1 and 2, we can derive this expression. Now, from this, when t equals to 0, Q equals to 0, and when t equals to t, Q equals to Q. Integrating on both sides, we get this expression. The final expression is Q equals to Q naught into 1 minus e power minus t by tau. What is tau? Tau is basically the time constant. What is time constant? The time constant can be defined as the time taken by the capacitor to charge to approximately 63.2% of the maximum voltage. Mathematically, the time constant is derived or given by resistance into capacitance, that is equals to R into C. This is the current voltage, percentage of maximum voltage and current at different time constants. For the current to reach maximum value, it takes approximately 5 time constants practically, and theoretically it takes infinite time. Now, during discharging condition, when the key K is released, the circuit is broken without introducing any additional resistance. And so, we can get that Ri plus Q by C is equals to 0. And R into dQ by dt, I can be written as dQ by dt plus Q by C is equals to 0. And after that, when T is equals to 0, Q equals to Q naught, that is maximum charge. When T equals to T and Q is equals to Q, integrating on both sides with proper limits from Q naught to Q and 0 to T. We get the final expression that Q is equals to Q into e power minus T by RC. This is the expression. Equation 5 gives the value of charge on the capacitor at any time during discharging, and when T equals to RC, that is one time constant, then this is the expression, which is 36.8% of maximum charge. During discharging, as Q is equals to Q naught into 1 minus e power T by RC or T by tau, what is the current? Current is given by I naught into e power minus T by tau. Just by differentiating this expression, we get the value of current. And during discharging, we get that Q is equal to Q naught into e power minus T by tau. And I discharging is given by minus I naught into e power minus T by tau. These are the expressions for current. So when we deal with graphs in charging, we see that charge versus time in capacitor. This is capacitor and this is resistor graphs. In capacitor, we see that there is an exponential increase in charge with time, with increase in time. And even voltage has the same kind of graph because these both have similar kind of expressions. In current versus time, in resistor, there is an exponential decrease. There is an exponential decrease because of expression for current is different. And voltage here is also decreasing, voltage versus time in resistor. Now, in discharging, these are the curves. V0 and tau, capacitor voltage and capacitor time, it is exponential decrease. In initial condition, it is maximum, and at final condition, it becomes zero. Final condition in the sense it is reaching, time is reaching to infinite. And in this curve, this is the current versus the time. And current is initially negative, maximum, and it is decreasing. And this is the graph for current versus time. Exponential changes happening there. This is the curve which we observe in a CRO when we connect an RC circuit. This is charging condition and this is the discharging condition. Now let us see some of the applications of RC circuits. So RC circuits are used in RC high pass and low pass filters. These are generally used in filters. As these circuits take a long time for capacitor to charge and discharge itself, they are often used as frequency filters. When the resistor is connected to the voltage source, these circuits are known as low pass filter. That means this capacitor allows only low frequencies to pass through it, and it does not allow the high frequencies to pass. And when this configuration is there, the capacitor will never get fully charged. And when the capacitor is directly connected to the source, then it acts as high pass filter. High pass filter, what is high pass filter? That means it allows only high frequency waves to pass through it, and it does not allow low frequency to pass through it. When low frequencies come to the capacitor, then what happens is that it becomes an open circuit, or its reactance becomes high, and it becomes like an open circuit. And when high frequency comes, then the resistor acts as a short circuit. So the high frequency curves or waves are passed through it. And some of the other applications include that they are used in traffic lights, they are used in pacemakers, and they are used in audio equipments. RC circuits can be used in places where signal filtering is needed, as we already saw, and it can be used as an integrator or differentiator. What are the challenges faced using these RC circuits? Component tolerances. When designing RC circuits, it's essential to account for the tolerances in resistor and capacitor values. Slight variations in these components can impact the circuit's performance, especially in precision applications like oscillators and timers. And even small change in the resistance and capacitor values, then there will be a large difference, or there will be variation in precision of these values. Then the applications like oscillators and timers which work on these values will have to change, and it will have to impact that. Temperature effects. The resistance and capacitance values may change with the temperature, affecting the time constant and overall performance of the circuit. With temperature, if these values change, then it affects the time constant and performance. Engineers must design the circuit that maintains a stable performance over a wide range of environmental conditions. So engineers have to make such circuits or such designs such that there is a wide range of environmental conditions they may be applicable. Conclusion. Giving it a final thought, RC circuits are foundational to modern electronics and are used in variety of contexts, from basic circuit design to advanced applications in telecommunications, signal processing, and power management. By understanding the principles of RC circuits, including their exponential charging or discharging behavior and the significance of time constants, engineers can design efficient and reliable systems that meet specific performance requirements. Looking forward, as technology evolves, RC circuits continue to play a crucial role in emerging fields like Internet of Things, devices, smart sensors, and energy efficient systems. This will remain essential in controlling and managing electronic signals and power systems, making a solid understanding of these circuits a key skill for future electronic engineers. Thank you.